Good morning, students. In the previous class, we have learned that magnetism as such is a microscopic property. That is, magnetic property in each of the material is caused due to the magnetic property of electrons inside the atoms. So in this lesson, what we are going to do is we will derive expressions for the magnetic moment due to the orbital motion of the electron and also the spin motion of electron. And then we will see Earth as a magnet, and also we will define few quantities which are related to magnetism. So first we will have a quick recap of what we did in the last class. That is how we derived the orbital magnetic moment of electron. So let me share my screen. Okay, so can you see the screen now?
Yes, teacher.
Yes.
Okay, so we learned in the last class that as every atom contains some electrons revolving around the nucleus, the electrons, you know, they are negatively charged. So there are charged particles moving around the nucleus, as you can see here. So when the electrons move around the nucleus, it is similar to a current carrying loop, a circular current carrying loop. So due to any circular current carrying loop, there will be a magnetic field at the center of the loop. So we derived in the last class an expression for the magnetic field at the center of the loop, which I have shown here. Here you can see from Biot-Savart law, we know that the magnetic field at the center of any current carrying coil is B is equal to mu naught I by 2R, where you know mu naught is permeability of free space and its value is 4 pi into 10 raised to minus 7. And I is the current through the loop and R is the radius of the circular loop. So here,
Teacher,
yes.
waiting teacher.
Okay, I will admit them. Okay. Now we will see here that the current means charge per time. So current is charge per time. If T is the total time taken by an electron to make one full revolution, then time is equal to distance divided by velocity. So we know that if you have a circle having radius r, the total distance of the circle will be equal to the circumference of the circle, which is 2 pi r by velocity. So if I substitute t is equal to 2 pi r by v in the expression for current, we will get that I is equal to EV by 2 pi r. Here, instead of t, I have put 2 pi r divided by v. So we will get this expression for current, and we substituted current's expression in the magnetic field. So mu naught by 2r, and instead of I, we have put EV by 2 pi r. So here we have 2 times 2, 4, and r occurs twice, so r square. So this is the expression for magnetic field produced at the center of a current coil, carrying coil, which is the magnetic field produced by an electron at the center of an atom. Is this part clear to all of you?
Yes, teacher.
Teacher,
Yes,
can you
teacher.
repeat from the second one?
The second one means time.
Yeah, this one.
Time taken by the electron to make one complete revolution. Time, you know, is equal to distance divided by velocity. So what is the distance when the electron make one complete revolution? That is the path length of the circle, which means the circumference of the circle, which is 2 pi r, if r is the radius. So time I have written here is distance by velocity. Distance is 2 pi r divided by velocity. And then I have substituted the expression for time in current. So current I is equal to charge by time. So charge is E divided by 2 pi r by V. So E divided by 2 pi r divided by V. So V goes to the numerator here. So we got the expression for current. Now what we have done is we have substituted the value of current in the magnetic field. B is equal to mu naught by 2r into I, right? So B is equal to mu naught by 2r. Instead of current, I have put EV by 2 pi r. So we got it as equal to mu naught by 4 pi, because 2 times 2 is 4. Then pi, then r times r is r square. Is it clear to you now, Irfan?
Yes, teacher, it's clear. Teacher,
Okay.
we can
Yes.
replace mu naught by 4 pi as a constant, right?
Mu naught by 4 pi is a constant. What is the value?
I think
10 raised
10
to
raised to minus 7.
because
minus
mu
7.
naught is equal to 4 pi into 10 raised to minus 7. So this is a constant value. Its value is 10 raised to minus 7. Of course, you can write like that. So let us now see the magnetic moment or the orbital magnetic moment. Due to the orbital motion of an electron, we know that any body which is making a circular motion will have an angular momentum. Here the angular momentum is represented by L. Angular momentum, you know that, is equal to the linear momentum R cross P, where P is the linear momentum. So here, you know, momentum is m into v. So the linear angular momentum will be equal to m into v into r, where r is the radius. So due to this orbital motion of the electron will have a orbital magnetic moment. So we are trying to get an expression for orbital magnetic moment of an electron, which is represented by mu L. Mu represents magnetic moment and orbital magnetic moment by mu L. L because it is due to the orbital angular momentum of the electron. So mu L is equal to IA. From where did I get this expression? We already defined magnetic moment M is equal to NIA, where N is the number of turns in the current carrying coil. Here we are considering one single electron revolving. So we can consider that as one turn. So we took N is equal to 1. And then we took, instead of I, current, the expression which we derived here. I is equal to EV by 2 pi r. And A means area. What is the area of a circle having radius r?
Pi r square.
Pi r square. So we got the orbital magnetic moment of an electron as EV by 2 pi r times pi r square. So pi gets cancelled and one of the r gets cancelled, and you will get mu L is equal to EV into r by 2. Because pi and r in the denominator cancelled with pi and one of the r in the numerator. So we got mu L is equal to EVR by 2. Now, in order to bring in the angular momentum, I want mass m here. So what I'm going to do here is I will be multiplying and dividing this expression with m, mass of an electron. So there comes one mass in the denominator and also one mass in the numerator. So this expression will become E by 2m times mvr. And you know mvr is L, the angular momentum, right? So I have substituted instead of mvr, the angular momentum L. So I will get an expression mu L is equal to E by 2m into L. But both angular momentum and the orbital angular momentum are vectors. So this minus sign shows that they are in opposite direction. Here you can see a figure where an electron is revolving with the velocity v and along an orbit having radius r. So this motion of an electron in this direction will cause a current in an opposite direction. And there is the angular momentum of an electron, which is represented by L, which is pointed outwards. You know that L is equal to R cross V. So if you take the vector cross product direction, if you curl your fingers from R to V, your thumb should point in the upward direction. You can take your own right hand and try to curl your fingers from the direction of R to V. So you can see that your thumb will point upwards. That is the direction of angular momentum. And this minus sign in the expression shows that the orbital magnetic moment of an electron is always opposite to the direction of the angular momentum. See, if L is upwards, mu is downwards. So remember that the orbital magnetic moment of an electron, because it is negatively charged, if this was caused by a particle which is positively charged, the orbital magnetic moment will be in the same direction as the angular momentum. But electron is negative charge, so minus E by 2m into L. So from this vector equation, it is clear that the orbital magnetic moment of an electron is opposite in direction to the magnetic moment, angular magnetic momentum. Angular momentum of an electron. Is this clear to you, this part? The relation between
Yes.
orbital
Yes,
magnetic
Yes,
teacher.
teacher, clear.
and angular momentum. Now, you must have learned Bohr's model of an atom. According to Niels Bohr model of an atom, the electrons are revolving around fixed orbits around the nucleus. And one condition for a fixed orbit is that their angular momentum should be an integral multiple of h by 2 pi. That is second postulate of Niels Bohr. So the angular momentum L is equal to nh by 2 pi, where n is called the orbital quantum number. N goes from 1, 2, 3, etc. If n is equal to 1, it means it's the first orbit. If n is equal to 2, it means the second orbit. N is equal to 3 represents the third orbit, etc. And what is h?
The Planck's constant.
H is Planck's constant, having a value 6.63 into 10 raised to minus 34 if you express that in SI units. So you have the Bohr's postulate L is equal to NH by 2 pi. So I'm substituting in the expression for orbital magnetic moment of an electron. Instead of L, I'm putting NH by 2 pi. I'm not considering the direction here. I'm just taking the magnitude. So mu L is equal to E by 2m into, instead of L, NH by 2 pi. So we got the whole expression as mu L is equal to NEH by 4 pi m. 2 times 2 gives you 4. Now, for the first orbit, you know that n is equal to 1. So for first orbit, if we substitute,
Teacher,
yes,
the value of E is minus, right?
yes, I told
Then
you,
where is the negative sign?
I didn't put the negative sign because negative sign just shows the direction of the magnetic moment. Now I am concerned only with the magnitude of the magnetic moment. Of course, you are right. There is a negative sign and therefore the magnetic moment will be opposite to that of the angular momentum. But now I'm considering only the magnitude. That's why I didn't put for E minus. I just took its magnitude. Okay.
Okay,
So
teacher.
it is 1.6 into 10 raised to minus 19. And for H, I have substituted 6.63 into 10 raised to minus 34. And pi, you know the value. M, mass of an electron, is 9.1 into 10 raised to minus 31 kilogram. So here I have taken all the quantities in SI units. And so if I calculate, I will get the value as 9.274 into 10 raised to minus 24. What is the unit of magnetic moment? Ampere meter square. Why ampere? It's current times area. So ampere meter square. Now this quantity 9.274 into 10 raised to minus 24 is a constant, and it is called Bohr magneton. So the orbital magnetic moment of an electron in its first orbit is called Bohr magneton, and it is a constant value. Usually it is represented by the letter mu b. Now how can we get the orbital magnetic moment for a higher orbit? For example, I want to find the orbital magnetic moment for the fourth orbit. So what should I do?
You have to put
Place
n
the
equal
value
to
of 4.
Yeah, 4 into Bohr magneton. So 4 into this value. So we can get the orbital magnetic moment for any orbit using this value. Is this clear to you?
Yes, teacher.
Okay. So this is the magnetic moment due to the orbital motion of an electron. But we saw that as the electron revolves around the nucleus in its orbit, it's also spinning about the axis. So there is, in addition to the orbital magnetic moment, a spin magnetic moment. So let us see what is the spin magnetic moment. So the electron, spin, and magnetic field. So what is the contribution of electrons' spin due to the magnetic field produced by the electron? So while revolving around the nucleus in its orbit, electron also spins. And the clockwise spin is called up spin. So if I am looking from down here, I can see that if I'm looking from the North Pole here down, what will I see? I will see that the electron is revolving in the clockwise direction. So for electron which is spinning like this, the spin is called up spin. Now if I look from down here, I will feel that the electron is spinning in the anti-clockwise direction, which means it is called down spin. So there are two kinds of spin possible for an electron. One is clockwise and the other is anti-clockwise. The clockwise spin is called up spin and the anti-clockwise spin is called down spin. Okay? And the spin angular momentum is represented by S. I don't know why they choose L for orbital or angular momentum. Orbital angular momentum we represented as L, remember? And it was h by 2 pi for the first orbit, if n is equal to 1. And for spin angular momentum,
Teacher, can you repeat this topic?
what?
This one, electron spin and magnetic field. Can you repeat this?
Electron is spinning. So whatever motion electron have, if a charged particle is moving, it will produce magnetic field, right? So we saw that because of the orbital motion, revolution of an electron, it is producing a magnetic field and it has a orbital magnetic moment. Now we are telling that the electron is also spinning about its axis. That is another kind of motion, another kind of motion of the charged particle. So due to that spin motion also, there is a magnetic moment. So now we are going to derive an expression for the magnetic moment due to the spin motion. Okay. So
Yes,
we
teacher.
have already derived earlier the magnetic moment due to the orbital motion, that is revolution. Now we are going to derive an expression for the magnetic moment due to the spin motion. So any electron which is spinning will have its spin angular momentum S is equal to h by 4 pi. Angular momentum L was h by 2 pi for the first orbit. Here you can see that there is no n, which means the spin angular momentum does not depend on in which orbit it is. Whichever orbit the electron is spinning, its value is a constant and it is h by 4 pi. What is h? Planck's constant. So 4 and pi are constants. So the angular spin angular momentum of an electron is a constant. It is h by 4 pi. And the spin magnetic moment, which is represented by mu s, is equal to Bohr magneton. That is the orbital magnetic moment in the first orbit of an electron. So we are taking here for spin magnetic moment EH by 4 pi m. You need not derive how you got this. That's out of the scope of your grade level. So you just have to remember that the spin magnetic moment is equal to Bohr magneton. So we got Bohr magneton in the previous screen. We saw that it is EH by 4 pi m. But you know that h by 4 pi is equal to s. So we can write it as E by m into s. Instead of h by 4 pi, I have substituted s. And again, you know that spin magnetic moment is opposite in direction to the spin angular momentum. So spin magnetic moment S mu s in the vector form is equal to minus E by m into s. As you said earlier, it's due to the negative sign of the charge of an electron. Is that clear? This just represents the magnitude, while this represents the vector form of the equation. And this again shows that the spin magnetic moment is opposite in direction to the spin angular momentum. Is this part clear to you?
Yes, teacher.
Okay. So we found two magnetic moments. One is due to the orbital motion. Another one is due to the spin motion. So the total magnetic moment of the electron is the sum of that due to the orbital motion and due to the spin motion. So you will get that as equal to minus E by 2m into L minus E by m into S. You just have to add them together. So here, what I'm going to do is I am taking minus E by 2m out of the bracket. So here I don't have E by 2m. So what I have done is I have multiplied with 2 and also divided with 2. So the 2 with which I multiplied this term, I have taken it along with s, and the one which I have put in the denominator, I'm taking out along with E by 2m. So here, when I take E minus E by 2m outside, I will get mu is equal to minus E by 2m into L plus 2s. So what is the total magnetic moment? What is the total magnetic moment? Mu is equal to minus E by 2m, where L and S you have. Okay, Hasina, tell me what is L? What is L in this expression? Hasina, tell me what is L?
Teacher,
Yes?
teacher, I have a doubt.
Yes, tell me.
Teacher, you said in the previous, I mean, you said yes, that minus will be not included in the magnitude part, right?
Yeah, but here I have
But here,
expressed, right?
yeah,
Yeah, I have expressed. Okay, I forgot to put the vector sign here. That's all. This is supposed to be a vector equation. I forgot to put an arrow mark here. So here it is vector equation. Consider arrow mark here. Okay, this is a vector equation. See here and here I put. Here I missed. So what is L? Who can tell me what is L?
Angular momentum.
L is the angular momentum. And what is S?
Spin angular momentum.
Spin angular momentum. You can tell L is the angular momentum, but in this case, it will be better if you tell L is the orbital angular momentum. Okay? L is the angular momentum due to the orbital motion of electron. So L is the orbital angular momentum and S is the spin angular momentum. So you will have to memorize this expression. Is this clear to you?
Yes, teacher.
Yes. So that if there are two electrons having opposite spin, then see the magnetic field produced by one is upwards, the another one is downwards. So when they are near to each other, they will mutually cancel. So all the atoms which have even number of electrons will have their spins in opposite direction, and so they cancel each other. So if you take an atom with even number of electrons, even though each one of them produce magnetic field, they are in opposite direction and then cancel out. So there is no net magnetic moment. Okay, and when you take materials with even number of electrons, they do not have net magnetic moment and they are called diamagnetic materials. Dia means two, right? So they have even number of electrons and their magnetic moments cancel out because they are in opposite direction. The magnetic field produced by them are in opposite direction. Now, if the atom has odd number of electrons, then there will be a net magnetic moment. Such materials are called paramagnets. So we will deal more about the classification of materials according to their magnetic property later, and then we will discuss about that in detail, and we will learn in detail about diamagnetic materials and paramagnetic materials. Just want to show you that it is caused due to the spin magnetic moments being in opposite direction for up spin and down spin. Okay. Now, let us consider the Earth's magnetism. So, I hope you know that if we have a bar magnet or a magnetic needle, and if you freely suspend that, then it will align itself in the north and south direction of Earth. So this idea was used by navigators from very old days, and they used it to show the direction when they traveled. So this is because the Earth itself behaves like a magnet. Here you can see a picture of Earth, and here you can see small rhombuses. They are magnetic compass. The red side represents North Pole and the green side represents South Pole. So here you can see when they travel, they held the magnetic compass on the surface of Earth, and it always pointed in the north, pointed along the geographic North Pole, and the green part, that is South Pole of the magnetic compass, pointed in the geographic South Pole. That is how when they travel through sea and all, they cannot identify the path. So they always use this magnetic compass to show direction. So from years back, we already know that Earth has this magnetic property. Now, why Earth behaves like a magnet? It's because here you have the inside of Earth. There is a crust, stiffer mantle, liquid outer core, and solid inner core. this liquid outer core consists of molten iron and nickel. And it's in the liquid state, which is under high pressure and very hot. So this molten nickel and iron may be existing as ions and full atoms. So they will be in constant motion because it is very hot and they are in the liquid state. So when these ions, charged particles, are continuously moving, it produces magnetic field. And Earth behaved as a huge magnet. So why Earth behaves as a magnet? Its core is made of molten iron and nickel, which are moving, and it produces the magnetic field. Therefore, the Earth behaves as a magnet. Now, what part of the magnetic compass is attracted by the geographic North Pole? North, right? So if the Earth itself is a magnet, if Earth was a bar magnet, so the south pole of that magnet will be attracted by the geographic north. So, and the north pole of that bar magnet will be attracted by the geographic south, right? So, actually, even if we mention the geographic north and geographic south pole as north seeking pole and south seeking pole, we named like that. Later we realized that if Earth itself is a magnet, then its south pole will be attracted by the compass south pole will be attracted by the magnet Earth's north pole, and the compass north pole will be attracted by, the compass south pole will be attracted by the Earth magnet's north pole. So there was a difference in the name given. The geographic north pole is actually the south magnetic pole. If Earth was a magnet, it will be its south pole. That is why the compass north is attracted by Earth. And then here, the geographic south pole will be the north magnetic pole. So the geographic south pole of Earth is magnetic north pole, and the geographic north pole is the magnetic south pole. And they are not exactly the same. There is a small angular difference between the geographic north pole and the magnetic south pole. And that angle is 11.5 degree, which is a constant. Is this clear to you? Why the geographic south pole of Earth is magnetic north pole? Is that clear?
Sir, not fully. I mean, I didn't understand properly. Can you repeat that part?
Yeah, let me show you something. Okay. Suppose you have a magnetic compass. Okay, let me consider this as a compass. Now I have this as a earth surface. If you keep this, Earth is a bar magnet. Earth as a whole acts as a bar magnet, right? So if I place a compass here, the north pole of the compass should be attracted by the south pole of Earth, right? So
Yes.
without realizing that in the beginning, people named the pole on the Earth which attracted the north pole of the magnetic compass as geographic north. We call it North Pole because the compass, magnetic compass, North Pole points towards it. Later we realized that if Earth is a magnet, it should be attracting the south pole of Earth will be attracting the north pole of the compass. So if you consider Earth as a magnet, its south pole is at the geographic north pole. Then is it clear?
Yes.
Hello?
Clear.
Yeah. So the reverse occurs on the other side also. So geographic south pole is actually, if Earth is a magnet, its north pole. So this name of the geographic north and south is usual North Pole and South Pole, which we generally refer. But if you consider Earth as a magnet, it's the reverse. And they are not exactly aligned. There is a small angular difference between them, what we actually considered as the North Pole and the actual South